So it's 1:10, and now just before the invited talk, we have Elena ready with her slides. And Elena will talk about the Lyman alpha measurements, so foremost interstellar hydrogen from an interstellar probe. So please take it away, Elena.
Thank you, Pontus, and thank you, Andre, for a very nice talk. And I think it very nicely leads to my presentation. If Michael, you could make it to the full screen. So yes, as Pontus said, I will talk about the great opportunities on Interstellar Probe to measure Lyman alpha emission, backscattered Lyman alpha emission, and understand properties of interstellar hydrogen all the way from the sun to the interstellar medium. So this is just a quick outline. I will start with the background. What is the backscattered solar Lyman alpha emission is, and how does it help us to understand properties of interstellar hydrogen. And also then I'll talk about previous discoveries that were made and limitations, and what are the open science questions, compelling science questions that we can answer with this type of measurements. And I'll talk about instrument requirements, instrument solutions, trades, and technology development. So next slide, please, Michael. Okay, so some of the background. So the sun moves through the very local interstellar medium, which is a weakly ionized plasma and mainly consists of hydrogen atoms. And those atoms, they have very large mean-free path, meaning that they can travel through hundreds of astronomical units, and they can actually move very deep into the heliosphere, where their properties can be measured directly, as Andre very nicely described to us with the neutral mass spectrometer or ENA low camera, or the properties of interstellar hydrogen can be measured remotely by measuring emission from hydrogen atoms. So these solar Lyman alpha photons are effective. So this is the wavelength 121.6 nanometers. So those photons are effectively backscattered by interstellar hydrogen atoms if they're within with the velocity within the solar Lyman alpha line. And the spectral properties of this backscattered Lyman alpha emission, such as line width and line shift and overall line shape, line profile, depend on velocity and spatial distribution of interstellar hydrogen inside the heliosphere. So Lyman alpha data provide us very important information about hydrogen properties, which are inside the heliosphere. Those properties are they're drastically different from properties outside in the local interstellar medium, due to interaction and charge exchange coupling with plasma as hydrogen moves from the interstellar medium into the heliosphere. And on this plot on the left, you see this global interaction. So the interstellar medium coming on the right, and you see the sun in the center. And here I'm showing this sort of different populations of interstellar hydrogen. And this division is sort of is made for simplicity, and it's useful sometimes to use these different populations in global simulations. So we have the pristine interstellar hydrogen. Those atoms, they can, again, due to large mean-free path, they can move directly inside the heliosphere. And also, as we go closer to the heliopause, those pristine hydrogen atoms, they charge exchange with the interstellar plasma, which is decelerated as it flows around the heliopause from outside. It's decelerated and heated. And because of this charge exchange process, you have the so-called secondary interstellar hydrogen. Those atoms are different from pristine because they're slower down and their temperature is higher than pristine hydrogen. Also, the charge exchange process between interstellar hydrogen and plasma protons in the helium sheath creates so-called hot helium sheath hydrogen, which is marked by number 3 in this picture. So inside the heliosphere, and also of course inside the termination shock, we also have the charge exchange process that creates very fast hydrogen atoms. Those cannot be measured with Lyman-alpha emission because those atoms are outside of the solar Lyman-alpha line, emission line. So we have the mixture of these 3 hydrogen populations that we can measure their properties through measurements of backscattered Lyman-alpha emission. And here on the right, you see the line profile, and this is the simulation. This is a simulated Lyman-alpha line profile for the observer at 1 AU. So you're sitting at Earth, you're looking toward the nose of the heliosphere, and this is what the model predicts for the observation of the line profile. And you can see how different populations of hydrogen atoms contribute to this line shape. So you see the dash dot line. This is the original pristine hydrogen, the contribution from original pristine hydrogen. Then the dash line, which is actually, it deviates from this nice Maxwellian. This is the contribution from the secondary hydrogen atoms created outside the heliosphere in the hydrogen wall. And also the dotted line, this is the contribution from hydrogen atoms created in the helium sheath. So this is what we expect to see if we measure line profile from 1 AU. Next slide, please. There were many great discoveries that were made with previous observations of backscattered Lyman-alpha emission. So SOHOS-1 observed all sky in intensity, in Lyman-alpha intensity, and also had the hydrogen cell on board to measure the line profile, although with limited wavelength range. And so these observations really brought many fantastic discoveries. So analysis of SOHO-1 data revealed the existence of those secondary hydrogen population created outside the heliosphere in the hydrogen wall. Those atoms, they're slower and hotter than pristine interstellar hydrogen. Also, with the use of hydrogen cell, it was possible to discover that the flow of interstellar hydrogen in the heliosphere is deflected from original flow in the interstellar medium by 4 degrees. And you see the result of this work on the right plot on the top. This was a great discovery, and it actually constrains the direction of the interstellar magnetic field. Also, the analysis of SOHOS-1 data showed that the interstellar hydrogen inflow longitude is stable over 20 years of this data. However, these are all fantastic discoveries and findings. However, the limited spectral data obtained from hydrogen cell on SOHOS-1 left us many open unanswered questions. For example, what's the spatial and velocity distribution of interstellar hydrogen in the heliosphere? And what does it tell us about charge exchange coupling at the heliosphere boundary and beyond? Also, what are the effects of these different hydrogen populations on the global interaction? And what is the structure and properties of the hydrogen wall, and how the heliospheric hydrogen wall relates to similar structures around other astrospheres? And also, is there any inhomogeneities in the local interstellar medium? And also, I would like to mention the observations of Lyman-alpha that were made in the outer heliosphere from Voyager 1 UVS instrument, and also ALICE on New Horizons that we heard already in this workshop. And both data from both instruments imply that you need an additional, to explain the variation of Lyman-alpha intensity versus distance, you need additional few tens of Rayleighs signal which is non-heliospheric. It could be galactic or extragalactic. And actually, if we could resolve the spectrum of Lyman alpha emission, that would really give us a definitive answer about the source of this additional Lyman alpha emission at large distances from the sun. Next. So this is the Interstellar Probe Science Traceability Matrix that you saw already. And next. And here's the column for the Lyman alpha measurements. And in the next slide, please, I'll talk about the compelling objectives. So these are compelling science objectives for the interstellar probe that would require making higher spectral resolution measurements of Lyman alpha emission on board of trajectory from outward trajectory from the sun. So these are to determine the properties of interstellar neutral hydrogen in the heliosphere beyond the solar ionization cavity. And I think I did not mention, so the cavity around the sun is where all hydrogen is ionized because of the photoionization and charge exchange process. And this cavity is about 1 to 2 astronomical units of size around the sun. And of course, it varies with the solar cycle. Also, to determine the processes and particle origin across the heliosheath that uphold the force balance and their global manifestation. And this relates to the ability to determine the properties of hot hydrogen atoms that are born in the heliosheath. Those atoms form the wings of the Lyman alpha line profile, as you see on this plot on the bottom. Also discover and characterize the properties of the hydrogen wall, which is shown here on the right, and also determine the properties and inhomogeneities in the very local interstellar medium once we are beyond the heliopause. So these are all compelling science objectives. And so now let's move to the instrument requirements. Next, yes. So this table lists the Lyman alpha instrument requirements. So our goal is to measure Lyman alpha line profiles in different directions in the heliosphere from nose to tail. And we will use those measurements to quantify velocity distribution of interstellar hydrogen in the heliosphere. So we want to have a high resolution, which is 0.002 to 0.004. And this is the resolution which is required to separate the contribution from different hydrogen populations into the Lyman alpha line. We want to cover many different directions, and of course the nose of the heliosphere, the tail, and also the crosswind directions, which are perpendicular to nose and tail. So previous measurements of line profiles with the H-cell on SOHOS 1 instrument, they showed the considerable variations of the line characteristics, line width and line shift from year to year. So there were solar cycle variations. So we think that monthly cadence would be sufficient to probe possible variations due to solar cycle effects within a year. So we require monthly cadence here. And the mass allocations and power allocations, 12.5 kilograms and 12 watts. Next slide. So here are the instrumentation options for this type of measurements. These are HL UV spectrograph to resolve a line profile. So this is the spectrograph that includes a far UV spectral channel with HL grading to resolve hydrogen and also deuterium Lyman alpha lines. And here on the bottom on the left, you see the MAVEN IUVS instrument, and also the measurement from IUVS. This is the spectrum of interplanetary hydrogen Lyman alpha emission observed by IUVS with HL grading in December 2013 during the cruise to Mars. So they were able to make measurements of interplanetary Lyman alpha. And the resolution achieved with HL grading in this instrument was about 0.008 nanometers. And also HL gratings were implemented in Hubble space, on instruments on Hubble Space Telescope. Another option is this spatial heterodyne spectrometer. This is a promising instrument solution with a compact design and high resolving power. And this is currently under development for laboratory tests and sounding rocket flights. Next, please. Okay, so we looked in instrument trades. So the first trade is high resolution spectrograph versus photometer. So measuring spectral, doing spectral measurements versus doing just intensity measurements. And this table nicely summarizes what we can achieve with different type of measurements and also different type of instrumentation. So with both spectral and intensity measurements, we can determine hydrogen density. But if we want to also determine velocity and temperature and constrain the distribution of interstellar hydrogen, we require spectral measurements. This cannot be done with intensity measurements. Also the same for being able to separate different hydrogen populations and see their variations, the variations in their contribution to the line profile with distance from the sun. We also require spectral measurements for that. For the hydrogen wall, once we are outside of the heliosphere, we will be able to look in different directions through the hydrogen wall and reconstruct the three-dimensional structure and determine properties in different directions through the wall. And so this requires spectral measurements. With intensity measurements, we will be able to determine the location of the hydrogen wall peak density and also the width of the hydrogen wall. And Olga Katushkina presented last year that this is feasible to do if we take intensity measurements toward the nose and toward the tail, take the ratio, and we measure this ratio as we go through the hydrogen wall. But we would not be able, with intensity measurements at the hydrogen wall, we would not be able to infer any information about velocity and temperature of hydrogen in the wall. Another instrument trade we looked at is the high resolution spectrograph versus SHS. So currently on SHS, required resolution at Lyman alpha cannot be achieved, and that requires significant technology development. So this is the limitation related to the grading surface roughness. But the HL spectrograph is a feasible solution, but it will require downsizing. Next. And I know Alice will talk more about this tomorrow. So this shows where the Lyman alpha spectrograph would be located on this beautiful image of the spacecraft. And next, please. And so here's the technology development. So Interstellar Probe example, baseline payload allocation gives us 12.5 kilograms and 12 watts. So best current example for Lyman alpha spectrograph is Maven IUVS, which is pretty large and heavy, but the instrument size and mass, it can be greatly reduced. And there is also a need for a detailed study of the trade-off between sensitivity and size of the instrument package. And our colleagues at Boston University and also in France at LATMOS, they're planning to do this technology development. Next. And here's my summary. So spectral observations of backscattered Lyman alpha emission on Interstellar Probe will provide properties of interstellar hydrogen across hundreds of AU from the sun out to the interstellar medium. We require high resolution to separate different populations of hydrogen atoms that are created in different regions of the global interaction. And the instrument for these measurements can be built with current technologies, and the mass and size can meet accommodations with technology development. Thank you.
Well, thank you, Elena. Fantastic presentation, and thanks for assembling. What Elena has done here is just assemble a very, very nice international team with the experts as well. So thank you so much for this intriguing presentation. So
I think I actually forgot to thank all the people who were involved in discussions over the last couple of years. It was fantastic input and very valuable. Thank you all.
Good. So that concludes actually all the measurements presentations that we had for the baseline. Tomorrow we will then continue on that same sort of venue and pattern for the